morning, everyone. Welcome to the last day. We're going to start the first session with Sakura telling us about categorical symmetry.
Great, thanks very much. Thanks to the organizers, thanks to Jonathan, to Miriam, and everyone else involved for committing a year ago to doing this, and it's great, everything's continuing. I'll talk about categorical symmetries. So I think there was a subscript or an and geometric engineering, and I'll actually get to that at the very end. But well, I had made a very conscious choice to focus on this aspect, and I'll explain to you in a second. Anyway, so going forward, what I'll talk about is this work in collaboration with these amazing people, in particular Lakshya Bharadwaj, who's a postdoc in Oxford, then Fabio Puzzi, who is here in the audience from Padua, Federico Ponetti from Durham, Leah Bottini is my amazing student in Oxford, Jingchang Wu, also in Oxford, Ibu, who spoke already, and condensed matter theorist in Stockholm, Apoorv Tiwari. This is work that appeared in a collection of papers over the past year or so, but I'll focus on one particular aspect, which I'll get to in a moment. But I think we can pretty clearly just sort of, this is, actual data, evidence, there's something going on about generalized symmetries. We can't sort of ignore that. I think 2014, the citations to this paper have sort of gone up, and in past year, there's been sort of some kind of increase. I don't think we can extrapolate it being exponential, but there's certainly something happening. And also, whoops. Okay. Just the program of this conference also shows, in fact, there have been 9 talks generally on this topic and a whole lot of gong show talks. So clearly even the geometry in strings is getting sort of reeled into this topic. One of the driving forces in this field have been really these non-invertible symmetries in larger than 3 dimensions, or 3 and larger. And in field theory alone, in the past year, there's been a gazillion of papers on this as well. And the whole thing really goes back to this paper that I was just flashing the citations to with 2014, that really we should think of any topological operator in quantum field theory as a symmetry generator. And once you take this seriously, you automatically eventually led to these non-invertible things. But it starts off with higher form symmetries. These are groups. They act on p-dimensional extended operators. And so when you have a p-dimensional operator, it'll link with a codimension p+1 topological operator that generates this p-form symmetry group. And the group nature means if I smash two of these together, so these q-dimensional guys, and actually put them close and some correlate or whatever, then actually this is the same as inserting the product. So if I have G and H, I can also insert G times H. And that's again part of the group. There's some extensions to higher groups, which are not relevant today. But these non-invertible symmetries are relaxing this group-like nature. Namely, you take 2 of these, and you may get a sum, possibly with coefficients, of other topological defects of the same dimension. And perhaps surprisingly, these type of structures are really ubiquitous in quantum field theories. And for example, in very simple quantum field theories like Woody-Young-Mills theories. And it's a bit funny that we only discover them now in 2022 or 21. And there's also actually, this whole development has seen some nice science sociological bonus, because the condensed matter physicists and mathematicians have studied these types of structures. And now we are talking to all these people, and there's a lot of interesting interconnection between these fields. PH, quantum math, and math. Okay. So let me just give you a couple of examples, just so you see it's not some vacant kind of mathematical exercise. So the most well-known thing are these Wallinder lines in 2D rational conformal field theory. They go back to the early, I guess, 90s or something. These are topological lines in 2 dimensions. They fuse according to this sort of non-invertible fusion rule, where these coefficients here are just the Wallinder fusion coefficients that you get from a rational conformal field theory. In 3 dimensions, topological order is classified also by things like so-called modular tensor categories they're essentially also obtained by topological defects that have these types of fusions. But really the exciting thing is in 4 dimensions, now there are a huge number of constructions, but just to give you a flavor, the very first paper that really pinpointed that there's something going on is by a couple of people also here in the audience, where they looked at the O2 gauge theory. You take a U1, you do charge conjugation gauging, and then you find some very peculiar fusion. And that I think sort of alerted everybody thinking, oh, this is really weird. And can we understand this better? And indeed, if you generalize this to outer automorphisms, not just charge conjugation, but other kinds of outer automorphisms, you find generically, this will give you something non-invertible. And in this case, it's a non-invertible one-form symmetry. Then there are, of course, these famous duality defects that are non-invertible zero-form symmetries, for example. These are just a couple of examples that give you a sense of these are really 4-dimensional gauge theories with these type of gauge groups. They have these non-invertible symmetries. Okay, now what is the utility of these? Many people ask, okay, so you found these symmetries, what are they good for? Of course, there are many applications, but we just have sort of scratched the surface of that. I think in 2 dimensions, there are really sharp statements we can make. So for example, you can constrain the number of gapped vacua of a theory. For example, if you have the easing category as part of this sort of symmetry category up here, and this, oh gosh, this is so confusing. This one here, then in fact, you can say the number of gapped vacua has to be a multiple of 3. You can make much more clearer statements as well, but that's an example. And of course, in 4-dimensional theories, confinement, deconfinement also ties in very much with these non-invertible defects, as also Ibu was discussing in his talk. There are many applications by now in pH, very field theoretic sort of applications, neutrino masses, the non-invertible symmetry breaking, et cetera, And I think for this audience, probably the most exciting direction that I think there isn't that much been done yet is how does sort of this talk to the swamp plant? How do no global symmetries apply to these non-invertibles actually constrain things in the swamp plant? Anyway, so my title isn't non-invertible symmetries, it's categorical symmetries. So how do you go from non-invertible symmetries to categorical? It's maybe slightly tedious and technical, this distinction, but it's really, you start with a generic quantum field theory, and now you have topological defects of various dimensions from 0 to d-1, and they have fusion, and they may be non-invertible. And the question is, what's the proper framework to characterize such symmetries? So if I give you this sort of setup, and let's say they all form groups, like P-form symmetry groups, the obvious answer is group theory. And then I look at representations of these things and so on and so forth. But 100 years ago, almost exactly, this wasn't so obvious. Namely, according to Wigner in an interview in 1981, Schrödinger was the person who actually said, one should sort of, eradicate this Gruppenpest, which is like the group pest. The group theory had entered the field. Wigner had sort of studied multi-particle quantum mechanics using representations of Sn, and people thought this was just mathematical garbage. So we find ourselves in 2023, 100 years later, and now we have these non-invertible symmetries. We can ask, okay, what is the mathematical structure that actually governs these topological defects that have non-invertible fusion? And the math answer is, and mathematicians have worked on these things, these are higher fusion categories. And so this is where this word category really comes in. And the analogy sort of should be, we should be studying this on sort of a similar level to group theory and representations of groups. And of course, we all hate categories because, I used to hate them because they were like very vacuous. But I think at this point, I've reached the point where you just stop worrying and you just start loving categories. And I invite you to join me on this quest. So anyway, I have 2 movie references, this being the Academy Award weekend coming up, and how some of us are moving to LA in a week. So anyway, categorical symmetries, what are they? So a fusion P category. So this is not going to be just the one category, these are P categories. So what is this object? It's actually very simple. You start with a set of objects. They're P-dimensional topological defects. So think of some symmetry generator of a top dimension. And then there are morphisms between these p-dimensional objects. So two defects, dp, dp prime, will have a dp minus 1 defect between them. One morphism, and between these one morphisms, there can be two morphisms. And in this way, you get a Ukrainian doll, and it will look like something like this, right? So you have a defect. This is two-dimensional, for example, another one. Then there can be lines between these, and between these lines, there can be a local operator. So you get a object, one morphisms, two morphism, layered structure. So this is, for example, the case of p equals to 2, which is two fusion categories, which luckily actually have been studied by Douglas and Reuter relatively recently. And the theory has been developed there to some extent. So these will be relevant for certain physical applications. We don't just want topological defects. We actually also want to be able to fuse them, like we discussed in these non-invertible symmetries. So there'll be a fusion on the objects, and that can have sort of structure of sums on the right-hand side. But also now on, say, we have one of these one morphisms on these objects, then there needs to be also a fusion on these one-dimensional objects here. So if there's a fusion on the level of objects, one morphisms, two morphisms. But this is not completely unintuitive, right? You have symmetries, and then you can have sort of defects inside these symmetry generators, and I'd like to also define the fusion of these guys. This is so roughly the structure. And now this may sort of be extremely abstract, but what I'd like to do in the main part of the talk is actually give you some motivation how we should think about these. And they really come naturally from sort of gaugings of symmetries. In fact, just standard ordinary zero form symmetries. And this is what goes under the name of theta defects. And really they're called theta defects, these non-invertible defects, because they are generalizations of theta angles. Let me discuss this a little bit. So why do I talk about theta angles? Well, let's start with the Maxwell theory. So we have just U1 gauge fields, coupling, and theta angle. You can think about this theory as one which comes from gauging a theory that is trivial. It has a trivial global symmetry that acts on a trivial theory. So far, nothing exciting has happened. But now I allow myself to actually add what's called a symmetry protected phase. For this, background gauge field A, for this U1 global symmetry, I add this theta FH term. And now I gauge the U1 symmetry. And what I get is exactly Maxwell theory. And what happened is that this SPT phase actually just becomes the theta angle. And so this actually is sort of the ultimate, the way that non-invertible symmetries will appear, that we allow ourselves to stack with some kind of topological phase, gauge a diagonal global symmetry, and the resulting thing will then have some additional structures. In this case, it's a theta angle, so it's not that nice as a symmetry generator, but this is sort of the idea. So stacking U1 SPTs is engaging at the theta angle, and we'll generalize this to these sort of topological defects in quantum field theory. So what are these theta defects? Well, they're simply start with a theory with some zero form symmetry. And now we actually take the product of this theory with a p-dimensional GTQFT. So just a TQFT, which will protect also this G symmetry. And then I gauge a diagonal G symmetry. What happens is in this gauged symmetry now, this topological field theory here becomes part of the theory and becomes actually a symmetry generator. So by starting with something that is sort of, has just convertible, say G-type symmetries, now actually I get these topological defects, and they will generically have non-invertible fusion. Sure.
So it's not really interesting that the boundary defects is topological. So it's big families.
Yeah, how would you? Yes, you can totally also do this with absolutely. But absolutely, so you can also stack just a G QFT and get actual defect operators in this way. Completely, yes. You can also look at non-topological versions of these theta defects. Absolutely. Here, I'd like to focus on sort of TQFTs, though.
The reason I asked the TQFT, the theory you put for Volkswagen, spectrum representation.
Yes. This is I will discuss the Wilson line momentarily. This is exactly the example that motivates why this actually is a sensible thing to do. So as Jake was just saying, let's look at sort of the simplest possible case where we have sort of Wilson line that we're adding as a dual symmetry. So let's start with a two-dimensional theory, zero form symmetry G, and that's generated by topological lines D1, right? So in two dimensions, zero form symmetries are generated by topological lines, and they have just this group-like fusion. And categorically, has a name. This is just G-graded vector spaces. It has sort of this, what I wrote down here is precisely the category vec G. So now we'd like to gauge G. So what we usually would do is we introduce a dynamical gauge field, and then we can write down Wilson lines, and representations are trace R e to integral A, and these are D1 Rs, and now we ask how do they fuse? Well, they'll fuse according to the decomposition of the tensor product of these Wilson lines, and this is a non-invertible fusion, and this category of topological lines is actually called now rep G. This is just from vec G to rep G as you gauge G. For abelian groups, the nice thing is, of course, that rep G is just characters, and that's just isomorphic again to the group itself. But in general, when G is non-abelian, like S3, this is not the case. Okay, so how does this now work in terms of zeta defects? I can think of the same problem, 2D theory, zero form symmetry, you start with vec G. Now we're saying, let's stack 1D TQFTs, the G symmetry, and gauge the diagonal. So this is the picture. And now the claim is these are precisely going to be these Wilson lines. Well, I'll need to tell you first, what are these 1D G TQFTs? A 1D G preserving TQFT is basically characterized by the number vacua and how G acts on the vacua, aka these are just representations again. So in fact, exactly these guys here will be precisely these Wilson lines I constructed earlier. But the nice thing about this picture is you can now generalize this to higher dimensions, right? So this is sort of something that works now in any dimension for any types of tautological defects. So the theta defects is we start with a theory, we stack on top of it a TQFT with G symmetry, gauge the diagonal G, and then these become topological defects in the theory. So the first interesting case is 2D GTQFT. So think of a three-dimensional theory with a zero form symmetry G. And so we have these now surfaces that generate the zero form symmetry, they have group-like fusion, and just like what we called vec G, now there's actually this whole structure is called 2-vec G. So this is another now a 2 category. You have surfaces, you have basically lines on these surfaces, but in this case, everything is very trivial. Everything is group-like, and then you also have local operators. And now we can gauge G using this theta defect prescription. And then the question is, what actually are now 2D GTQFTs? So here the story is a little bit more elaborate. It's mildly more interesting than in the 1D case. Well, basically, there are two effects. So there can be spontaneous symmetry breaking in a given vacuum from the symmetry G to some subgroup H. And in 2 dimensions, it can be H SPT phases, and they're just classified by some kind of 2-core cycle. So this sort of characterizes all the GTQFTs. And so what we'll get is these will now actually become the defects in the gauge theory. So let's look at the simplest example of G equals to Z2. In this case, there are 2 subgroups, H equals 1, H equals to Z2, and there's no co-cycle. And now we just go through all the machinery of TQFTs. There can be TQFTs with 2 vacua, where the symmetry is basically broken, and then there can be a TQFT with 1 vacuum, where the symmetry is unbroken. Whoops. And the interesting thing to observe here is that this one here, actually now we can compute the fusion, has this non-invertible fusion. So you have a 2-dimensional defect, and it fuses to 2 times itself. And this is actually nothing other than what mathematicians would call 2-rep Z2. And if you follow to this literature a little bit, you will also observe that this is precisely the fusion that you know from what's called condensation defects by these gentlemen here, where essentially we can think of this as there's a surface, and we've inserted a network of lines of the dual symmetry. So right, we were gauging a zero form symmetry in 2 dimensions. There'll be a dual 1-dimensional topological line, and we just inserted a match. And that's precisely this deep minus surface. But this is now an example of a non-invertible fusion that we get from this type of theta defects. In this case, these are just the condensation defects. Okay, so you've seen 1D TQFTs. We go from essentially something like VEC-Z2 to REP-Z2. So here we have these topological lines that are basically group-like again. For 2D, we have this 2-REP-Z2 with the non-invertible fusion. And more generally, in fact, you get these 2-REP-Gs, and you gauge a G0 form symmetry. So the burning question here is, of course, are there actually theories where these things are realized by actual quantum field theories? And of course, they are. And so you can now draw down these kinds of categorical symmetry webs where you start, for example, with 2-vec of, in this case, D8. This is a 3-dimensional gauge theory with a PSO4n gauge group. And now we can play this game. We can gauge this and go to a 2-rep. D8 is the pin plus 4n. We can gauge subgroups thereof and then sort of span out this network of categorical symmetries. And you'll see all of these are some 2 categories that are now symmetries of these quantum field theories. Of course, 3-dimensional SO groups aren't the most exciting things on the planet. So now one can actually look at also the D-dimensional versions of that. And the interesting thing is, right, so here we start with spin, SS, PSO, SOO, and so on and so forth. They will all have now these higher categorical symmetries. So these are really pure Yang-Mills theories with these gauge groups. Will have these higher categorical symmetries. So this seems a pretty complicated sort of picture. And so you can ask yourself, well, is there some sort of unifying way of characterizing this? I don't want to every single time write down all these different categories. And that actually leads us to the symmetry TFT. And we already heard about the symmetry TFT in various talks. But one sort of very quick way to explain what it is, it's the everything, everywhere, all at once of symmetries. Because it essentially answers a question that I think someone asked in one of the earlier talks is, if you have these different gauged versions, how should I actually think of the symmetry TFT? Well, it really encapsulates all of these things by just then slotting in different boundary conditions. So you really are seeing sort of, you know, I think Iñaki described this in his talk yesterday. There's a D plus 1-dimensional TQFT. I would like to think of it as there's a physical theory here, there's a topological boundary condition, and I essentially start with some categorical symmetry, right? So in the examples we've seen so far in this conference, this was always some kind of BF theory plus anomaly terms. Here, I'd like to just completely forget about any kind of Lagrangian theory that we might write down. It's just there's a categorical symmetry C. For example, one of these things that we had here. And then I'm asking, what is this symmetry TFT that now actually sits in this, or what are the topological defects of this D plus 1-dimensional theory that sits sort of in the bulk of this slab, where then I have on the one side here the symmetry C, and here the physical boundary condition. When I collect it, I then get exactly the theory with the symmetry C. And changing now the boundary condition here will change which categorical symmetry is realized. Like, for example, and in here, I could change the boundary conditions and map out this entire symmetry, categorical symmetry web. Okay, so this is sort of essentially encapsulating all the different global forms in a generalized sense. In 3 dimensions, this is what's called also very often the Turai-Vero theory for this fusion symmetry C. So you have some fusion symmetries, fusion category, and then there's a Turai-Vero theory, which is basically the SIM-TFT, or the topological defects of the SIM-TFT. More generally, this is the Drinfeld center of a fusion category, a higher fusion category. And for 2 categories, this is already quite an interesting thing to actually understand. So one way to think about this is we have objects that can either end on this topological boundary, so bulk objects in the SIM-TFT, or things that cannot end, right? So this is sort of the Neumann-Dirichlet boundary condition picture, but now sort of formulated in terms of the SIM-TFT. So if they end, they actually give rise to some charged objects, whereas if they don't end, then there'll be some junction to another topological defect, X, that is part of the symmetry category C of the theory. So you actually, in this way, characterize the symmetries by the different types of endings that these bulk topological defects of the SIM-TFT can have. Okay, so in fact, indeed, in this picture, C does not need to be invertible or anything. It can be any type of higher fusion category. And in 2D, in 4D, there's some examples in this KOZ2 paper, and we're just finishing some work on 2 categories more generally. Okay, so I told you a slide, I brushed over some aspects. And one thing is, theta defects are very general. You can really go through, I know it's fine. You can go through this in any dimension, and there'll be this sort of general theta defect construction. But if you hit 3-dimensional topological defects, something interesting can happen. Namely, you can have sort of 3-dimensional topological defects on which you don't just have sort of, this picture of n vacua with some G action. You actually can have 3D topological order. And that's sort of the speciality once you reach higher than 4-dimensional quantum field theories, that you can have 3D topological defects, which may not necessarily actually have gap boundary conditions. So these higher categories, as you go to 3 categories and higher, will have sort of some additional structure that comes from these sort of interesting 3D defects. And we've seen an example in Ibu's talk. So this is not formulated in this way, but it's exactly what this is. And this comes back to these mixed anomaly defects from Kaidimori and Zeng. So you look at a theory with 0 form symmetry Z to M, 1 form symmetry ZM, which enjoy a mixed anomaly, A1 Pont-Viagin squared B2. So the 0 form and the 1 form symmetry have a mixed anomaly. The point of this KOZ paper was the defect that generates the 0 form symmetry is basically not invariant under background gauge transformations in the presence of 1 form symmetry background. It transforms with this anomalous phase. So actually, if you wanted to gauge the 1 form symmetry, this would not be actually consistent. So what you have to do is you need to stack it with some 3D TQFT. But now, because you have this anomalous variation, the 3D TQFT has to have both a 1 form symmetry and also an anomaly. The anomaly needs to be canceled. So this is exactly the sort of twisted theta defect when you have these types of non-gap boundary, non-gap TQFTs. So in this case, it's just a U1 level M Chern-Simons theory that actually does the job. So you can think of these KOZ defects also in terms of twisted theta defects. So this theta defect of picture extends very naturally to include such things. And this is a very nice example. In this case, you have these non-invertible defects in the PSUM gauge theory. And you want to gauge the 1 form symmetry, which had this fusion that Ibu was already showing in his talk. Okay, so let me just now in the last 2 minutes, just give you just some thoughts. It's really nothing particularly profound, but we've already seen many talks by Ibu, Max, Iñaki, and I believe later by Sagar on how certain aspects of these categorical symmetries or non-invertible symmetries appear in string theory. I think the key question is, can we actually really derive from string theory these categorical structures, right? And not just sort of using field theory result to actually determine the answer. And just to illustrate this, I just want to show this in this example that Ivo also discussed in his talk. So we had these fusions of the non-invertible defects in 40n equals 1 superangles. But the nice thing is actually these defects, this fusion here really is modeled perfectly on the nose by string theory. Oops. So string theory, if I realize these in terms of branes, so the mantra of Ibu and Max and Iñaki's talk was, think of these as branes, as symmetry generators of branes. These fusions are on the nose realized by D5 branes, slammed together. There's flux on these. They will actually puff up and give D7 branes using the Myers effect. And that's precisely modeling this non-invertible fusion. So branes know about this. We don't need the field theory description. Likewise, if I take N with N dagger, that was a condensation defect for the 1 form symmetry. Again, the branes are very smart. I take a D5 and anti-D5, slam them together, and then one can show in this paper that's upcoming that this actually, by a tachyon condensation, is realized in terms of the D3 branes. So clearly, there's some structure that the branes in string theory know that realizes this categorical structure. And in fact, the interesting thing is to realize the SymTFT, what we really need is the action of topological defects on actual physical defects. And the beauty of this is that, in fact, that's realized also in string theory. So in this n=1 setup, what we'd like to understand is how Toft lines are acted upon by these non-invertible defects. So these guys here. So what we expect is there's some sort of written effect, we pass it through, and on the other side, this genuine line defect becomes a non-genuine one with a flux attachment. And if you think of the branes, the D3s realize the Toft line, the D5s realize this non-invertible defect, then this is precisely Hanani-Witten passing this through, generating in the process and fundamental string. So that's the action of a non-invertible defect on a physical line defect or an extended operator. And so string theoretically, it seems like the SymTFT, which knows about all these fusions, encodes these things. So I think the dream would be to really understand the SymTFT precisely from such a brane picture. How do we see all these fusion categories, structural objects, morphisms, higher morphisms encoded in the branes? And then finally, there seems to be really some nice relation between Hanani-Witten and this action of non-invertible operators on actual charge defects. That certainly seems worthwhile understanding. Okay, thanks very much.
Within theory,
Maybe you want to take a listen.
there's a theory that effects have to be inverted.
What?
There's a theory that effects have to be inverted.
The theory? Well, I don't think it has to, right? You mean like does the actual quantum field theory, right? You're asking. So for example, if I take a 6D theory, whether there, yes. I think Craig?
So it seems important for the unit space here. It's kind of how we use and super one of the dimensions. Using one of these. So with 3 more dimensions, like what's the limit of the dimensions?
Yeah. So this is true. So in fact, indeed, if you take, this is a question that I think Iñaki asked Ibu, when you take fusion of U1M with M odd or even, I forget, can we really work out, can we decompose this back into something just nice, right? That's sort of tricky. You know, this goes back to this Lam Sin Cyber paper from 2018 or something, right? I think that specific fusion, you can't maybe decompose into something nice. There's a paper by Pavel Putrov, who actually says, well, why don't you just sort of extend this? You know, here we are always stacking with a minimal TQFT. You don't necessarily have to do this. If you actually stack with something that's not the minimal TQFT, you get actually very nice fusions. And no one says that you should be just stacking with a minimal one. So there's some freedom, and I think it's interesting to understand how that actually, you know, can be made a bit more precise in terms of also this categorical way. Yeah, Jake.
Thanks. So we're not very nice thing regarding the student here we have the so going back to the local lines, so we discrete H theory, local line topological, they continuous H theory, we're going to one H theory, they're not topological. Even though the theory that is close to mine is a 0+1 G matter.
I have always, I might have not always super emphasized this, but these are usually for these G, when I say GTQFT, these are usually TQFTs for G finite. But I think it's super interesting to say you don't need to think about it. You can generalize this and in fact in this way systematically construct extended operators in quantum field theory, right? These are just then theta defects. I mean, you can just go in and apply the same logic. Absolutely.
Do we have any more questions? That's thanks for